All right, folks, it's back in action here. In this video, we're going to do two main things. We are going to look at one more example of writing a rule. This is a more advanced problem because notice that in each case, we are only given two random terms within the sequence instead of specifically be given the difference or the ratio from the beginning. So these are going to require a little more work. And then down here at the bottom, we're going to look at how to quickly add terms in a sequence. It is called a series if we add them up. So let's just jump into this next example of how to write rules for sequences, because these are all methods and situations that you will run into. So we want to first look at writing a general rule for, if I give you this, I want you to recognize that D is a clue, that this is an arithmetic sequence. Remember, arithmetic simply means linear. All we do is swap X and Y for something else. Over on the other side, we're going to have our general rule that R is our clue, and this is going to be our geometric. And we're going to remember that that is going to be exponential. It's just a really important idea that we want to get into our head early on. So instead of thinking of these as two brand new types of rules, we just connect them to something that we already know. It does make it easier. Notice I didn't give you the rearranged version here, but you could easily rearrange that if that suits you. We won't really need that, but remember we could write this as dn plus a sub 1 minus d. That was our rearrangement that we did on the other side. Okay, let's take a look here. This time I do need to tell you what type of sequence that you're working with, because otherwise you would not know based on the two terms which type of sequence that you had. Earlier we had other things in the problem that were a clue for us. So just like before, I find it very helpful if we just rewrite these as nice ordered pairs. It links us to something that we've already done before in the past in our mathematics experience. So if we know that an arithmetic sequence is linear, and I gave you two terms and told you it was linear, you would know that to write that equation for that line, you would simply need to find your slope. So slope is now what we're calling our difference, but the process is going to be the same. So we're just going to do our basic slope calculation, just like you've always done since Algebra 1. You calculate that slope. I've already done the math here. Feel free to pause if you want to check my calculations. And we will find that our slope or our difference is 5. Now we can go right back to what we did on the previous page, because now we have our difference and we have 2 points to choose from, and we can go right back to using that point slope form. So again, instead of y, we're going to write a sub n. So a sub n minus 54. Then we're going to put in our slope. Instead of x, we're going to write n. And now we're right back to rearranging it just like we did before. Quick doing that arithmetic, that basic algebra that you guys have done hundreds of times. Minus 6. I did not mean to write 54 there. Sorry, let me fix that. That was just supposed to say 5n. There we go. Oh my gosh, I did it again. 5n. There we go. 5n minus 6. Whew, that was rough. Okay, there's our general rule. Now, let's take a look over here for our geometric sequence. Again, if I only give you two terms, I'm going to have to tell you what type of sequence it is. The fact that it's fractions is not really our game changer thing that we might think it is. We can have fractions in an arithmetic sequence just as well. So for our geometric sequence, this one is definitely going to require more work. This is going to be a little different. Remember, this is going to be an exponential. For this one, if we want to do this effectively, we are actually going to use a little system of equations in a way that you've probably not seen before. So I'm going to say 3 and the 1/3. I'm going to say my 6 and my 1/81. Then I'm going to go ahead and I'm going to substitute everything I can into my formula. So I'm going to say 1/3. I don't know the first term. I don't know the ratio, but I do know that my n was 3, so I can say 3 minus 1. So this will become 1/3 a sub 1 r squared. Over here, I can do the same process, 1/81. I still don't know the first term. I still don't know the ratio. I have a different n this time, so I can write 6 minus 1. So this becomes 1/81 a sub 1 r to the 5th. Now, in order for me to solve this, I have 2 equations and 2 unknowns. I'm going to do a system of equations. Now, our normal elimination method is not particularly helpful adding these 2 together. So what I'm going to do instead is substitution. I'm going to take one of them. It's usually easier to do the one with the lower exponent, and I'm going to solve for a sub 1. So a sub 1 is now going to become, and I'm going to write this in a different way. I'm going to write 1/3, and I'm thinking I'm dividing by r squared, so I'm going to write 1/r squared, and that's going to equal a sub 1. Now I can take this whole thing and substitute it for a sub 1 over here. So it's going to look kind of complicated, but it's not actually as bad as it initially seems. So I'm going to have 1/3. I have 1/r squared. I have r to the 5th. I'm going to go ahead and put it over 1 because it makes the math a little easier to follow. And now I'm going to start cleaning things up. I don't like this 1/3, so I'm going to multiply both sides by 3, which means this goes away. And if I multiply 1/81 times 3, this is effectively saying this becomes 27. And of course, these reduce, and this exponent now becomes 3. So what I have is 1/27 equals r cubed. I can take the cube root of each side. So my r value is now going to be 1/3. And I'm actually going to, for the sake of space, I'm going to actually come up here, and I'm going to start writing the rule up here at the top. So I still don't know that first term, but I do know that my ratio is now 1/3 n minus 1. So I'm just going to fill that part in. Now, if I take this 1/3 that I calculated right here, and I now put that 1/3 in over here, I can solve for a sub 1. So a sub 1 is going to be 1/3, and then 1 over my 1/3 squared is 1/9, which means a sub 1 is 1/3. Sorry about the spacing here, guys. I'm going to multiply by this reciprocal, gives me 3. So my first term is now 3, and that gives me that rule. So we will explore writing these exponential equations more throughout chapter 3. The one that you should already feel pretty comfortable with is this arithmetic, because it's just a line. So if this one feels a little overwhelming, don't stress too much, because we're going to do more with that. Now, down here at the bottom, we're going to look at what are called series. A series, okay, a series is simply a sum. It means we're going to add up all the terms in a sequence. So a series means we're going to add the sums and the terms in a sequence. So this might be some new notation here. Notice here I did give you that rearranged form. This symbol called sigma, different sigma than you guys are probably saying these days. This sigma means to sum. It means to add things up. This K is the term number to stop. It's not a value, it's a term number. This is where we start. It's a term number to start. So This means we are going to sum, and this is an arithmetic rule, so we're going to sum an arithmetic rule. Now, the thing you really want is this lovely little formula right here. This is the formula to find a sum, okay? This n right here is how many terms we're going to add. Okay, so let's find one down here. Let's look down here, and if we look at all of these little sums, and then we look at the rules, only one of these rules is an arithmetic rule, and it's this one. So I have an arithmetic rule right here. This one is arithmetic. Which means we can use that formula from up above. So we are going to stop at the 35th term. Now, look at our little formula here. It says we need the first term, and this is the value of the term where we stop. So this is the term value. So if all I have is my rule, I need to know, in order to use my formula, I need to know what is a sub 1. And in this case, I need to know a sub 35. I need to know the first term and the 35th term. So let's calculate those just like we did at the beginning of the last video. So I'm going to have 6 minus 11, and then I'm going to have 6 times 35 minus 11. And if you type those into your calculator, you're going to get a -5 and 199. Now we just follow the formula. So the sum of the first 35 terms is going to be, how many terms are we adding? That's 35 divided by 2. And then inside the parentheses, we're going to put the first term plus the term value of where we're stopping. And if we type that in our calculator, you're going to get 3,395. So if we wrote out, no one wants to do it, but if we wrote out the first 35 terms of this sequence, boom, 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 all the way out, and then added them up, you would get 3,395. Okay, the next ones that we're going to look at, these are going to be sums of a geometric series. Now, for sums of geometric series, we have two types. We have a finite sum, meaning we have a start and a stop, and we have an infinite sum, which is a start, and then we go for effectively forever, okay? So the finite sums have a stopping value. The infinite sums will specifically say infinite. Now, when it comes to the infinite sums, we're going to have a little discussion right here. For right now, let's look at this one. So notice that this is a geometric rule, and then we're going to get a formula for it. So if you know you have a sum of a geometric rule, you follow this formula. So again, let's look down here. I have 3 more sums left. I'm going to look at all of these and say, oh, these are all geometric rules. Now, we want the one where we have a value on the top, not an infinity sign. So I have infinity, I have infinity. Oh, this is my finite geometric sum. Okay. This says that we're going to do 9 terms. That's what that is. So we're going to go from 1 to 9. Now we're going to follow our formula. Remember, this is the first term, this is the ratio. So everything that we need for our formula is right here. So to go ahead and do that, we are going to say our first term is 2. Now, the formula doesn't write this as over 1, but I'll be honest, I like to write this as over 1, and I even use little parentheses there. I find that to be much easier to work with. Then, the parentheses are going to be very, very important here. We are going to say 1 minus, and our ratio is negative, so we need to write that -5 in parentheses. we are going to raise that to the nth power, and the nth power here is the number of terms we're adding. So it's going to be -5 to the 9th. Then this is all going to be divided by 1 minus that ratio, which is a -5. This then is going to become 6. Okay. Now, if we type this into our calculator, and you have to be very, very careful with your parentheses here. If we type this into our calculator, oh, actually, I'm going to add one more thing here as just a reminder. We can also reduce our 2 and our 6. Let's go ahead and reduce that. We'll make this a 1, and let's make this a 3. And then we can go ahead and we can type this one into our calculator. And again, you have to be really careful with those parentheses, because if you're not careful with your parentheses, you're going to, you won't get the right answer, because remember, you have this negative ratio that you are raising to this 9th power. So you're going to have to be careful. 1 minus, be sure to type in your parentheses with your 9, and then you're going to divide that by 3, and you will get 651,042. It's a big number, okay? So because our numbers are going to grow pretty quickly if we're multiplying them effectively by 5 every single time. Okay, the last one that we're going to look at here are the infinite geometric sums, and this says that we are going to keep adding them forever. Now, we're going to have this idea of a converge and a diverge. Converge means that it will converge if the ratio is less than 1. It's going to diverge if the ratio is more than 1, in which case we would say that there is no sum at all, okay? Because the numbers are going to effectively continue getting so big that we can't actually get a total. It's going to go to infinity. That's what would happen, for example, here. So if we look at our remaining 2 that are both infinite, I want you to notice that these are both infinite sums. These are both infinite geometric. However, on this last one, part D, our ratio, which is R, is greater than 1. Therefore, we would say that this is going to diverge. Sorry about that. This is going to diverge. And we would say no sum is possible. The last one then is our infinite geometric, where the ratio is less than 1, and this will converge. And this is a really, really fast example, because our formula, you can see, is incredibly simple when it's going to converge. Our first term is 10. Our ratio is 1/7. So we're going to do 1 minus 1/7. I'm going to get common denominators here. So that's going to give me 10 over 6/7. I don't even need a calculator on this one, because 10 over 1 times 7 over 6, I can reduce this. This is going to give me a 3. This is going to give me a 5. And my sum will be 35 over 3. Okay, so I know that's a lot. We are going to apply this in class, and then we're going to continue to review this over the next couple weeks, especially these geometric sums. Okay, that's all we got.